In this section, we're going to look at problems that are called related rate problems. And as you can see here, related rate problems are those problems involving variables that are changing with respect to time. And if two or more such variables are related to each other, then their rates of change with respect to time are also related. The best way I can describe for you to imagine this is imagine watching a train. Suppose you're standing fairly close to the train tracks, let's say 20 or 30 feet away from the train tracks, and you start watching the train while it's a long ways away, and keep your body fixed to the train tracks, not turned one direction or the other. And only move your head. Keep your eyes fixed and don't move your eyes, only move your head. And of course, when that train's a long ways away, it doesn't, you don't have to move your head very rapidly. But the closer and closer that train gets, the more quickly you have to move your head. And then as the train gets almost upon you, then you're having to move your head very quickly to still watch the front of the train. Now, the train's not changing its speed in this case. Oh, speed is a rate of change, isn't it? But if the train is moving slowly, then, of course, your head will never have to move as fast. The faster the train is moving, then the more quickly you move your head, but you're moving your head at a different rate. So the rate that you turn your head is related both to the speed of the train and also how far away the train is from you. So this relationship exists, but it's not the same, it's not a constant relationship, although the speed of the train is moving constantly. Here's a quick little video just to remind you of what I'm talking about. Now, before we start these problems, I want to remind you of a couple of things. And we kind of saw this when we were talking about implicit derivatives. And these are some simple ideas that I just want to keep you informed of or keep you thinking about. The derivative of 2x with respect to x, of course, is just 2. But now compare that, and we've talked about this before, that if we take the derivative of 2y with respect to x, that is, when the variables don't match, then we have to use this implicit derivative idea. We're thinking of y as a function of x. We don't know what it is. In this case, that's 2 times the derivative of y with respect to x, isn't it? Now, there's nothing so special about x here. We could be taking the derivative of 2y with respect to t. So we would say the derivative of 2y with respect to the variable t. Well, that'd be nothing more than 2 times the derivative of y with respect to t. But, you know, what we haven't seen this before, but we could also find the derivative of 2x with respect to t. And the issue is that with respect to variable t and the variable we're finding the derivative of, when those don't match, then we have to use this implicit idea. So in this case, we're thinking of x as a set of parentheses, maybe, that has stuff about t inside of it. And so we have t at the 2 out in front of those parentheses, and then we have to multiply the inside of the parentheses. I mean, we have to multiply with the derivative of the inside of the parentheses, and the inside of the parentheses is that x. So this is actually 2 times the derivative of x with respect to t. Now, carrying that a little bit further, we could just ask, for instance, what's the derivative of 3y to the 4th power with respect to t? Well, remember how we did that in the implicit differentiation section. We'd take the exponent 4 and multiply with the coefficient 3 and get 12. We'd reduce the exponent on y by 3, but remember y is parentheses with t stuff inside of it now, and so we'd multiply that with the derivative of the y with respect to t instead of x, because what we're taking the derivative with respect to is the variable t. Similarly, we could ask for the derivative of, say, 5x to the 10th power, but with respect to t, not with respect to x. So that's not a normal derivative. We'd say 10 times 5 is 50. Reduce the power on x by 1, but remember it's with respect to t, so then we have to multiply with the derivative of x with respect to t. and we could continue with this idea. Now, what's important to recognize in the types of problems that we're going to be dealing with, like the speed of a train, well, the speed of a train is really is a rate, isn't it? It's the change in distance in some unit of time. That's what speed is, isn't it, or velocity. So what we're going to be needing to recognize is that when a variable, like an x or a y or whatever variable we have, like x or y, we'll say in this case, depends on time. And that's really what we're going to be dealing with here. Depends on time. Then the derivative of that variable with respect to t, so the derivative of x with respect to t is the derivative of y with respect to t. And of course, remember here, t represents time. Those derivatives are called a time rate of change. And of course, speed or velocity is one such time rate of change. So that's what we're going to be discussing. So let me start the first problem, and then we'll expand from there. Now here's our example 1A, because we're going to do a continuation of this problem. But as you see it stated, someone's dropping a pebble into a calm pool of water, and that causes ripples in the form of concentric circles. So you can imagine that. You drop it in, and there's first a little ripple that's small, and then of course it expands out, doesn't it? And then expands out further, and expands out further, and expands out further as the ripples travel through the pond. We've seen that many times. And the radius of the outer circle is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of this disturbed water changing? So that's basically the area of the outside circle. So that's the question that we have facing us. So here's what we do. And I'm going to try to lay this out in a way that will follow this format as much as we can all the way through. And usually the first step that we take, and I've drawn a little diagram of concentric circles, but the first step we take is the idea of, we'll draw a little diagram. And so we're talking about a circle here, okay? And remember that this radius is changing. Now, don't get carried away, because we don't want to say the radius is 4 feet. The radius is changing. We just want to know something about it when it is 4 feet. So don't label r as 4 yet, because again, that's something that's changing. And if we have a variable that's changing, we don't label it as a constant amount. Okay, so here we got our little diagram. Now here's the process that I would suggest that we go through. We want to first decide what information is given. And I'm going to actually say, what's the given rate? We have information that's given to us. And remember, we're talking about rates being something that's changing. We're talking about an issue of things changing with respect to time. And so, in fact, in this problem, it tells us something about a rate right there, doesn't it? A constant rate. Well, what is it? The radius of the outer circle is increasing at a constant rate of 1 foot per second. Now, here's the next thing we have to understand that we need to do. If we're going to call that variable r the radius, we need to talk calculus. And remember, rates are derivatives. So this is calculus talk. Calculus talk for rate. That's exactly what a derivative is a rate of change. So what we're given is that the rate of change of the radius with respect to time, or the derivative of the radius with respect to time, is a constant 1 foot per second. So we know dr dt is 1. Now, the next thing that we need to decide about what's supposed to happen here is, what is it we're supposed to find? You know, what is it we're asked to find? We're asked to find the rate, again, at which the total area of the water, of the disturbed water, of the circle, the outer ripple, find at what rate that area is changing. Well, if I'm going to let, of course, we already knew that R was the radius. I'm going to let A stand for the area. Okay, so I'm going to just make a note over here. A is going to represent area of the outside circle. And of course, R was the radius of that circle. And they're both changing. See, they're both changing because as time goes on, the radius is getting bigger, and of course, as the radius gets bigger, the area of the circle is getting bigger because we have a bigger circle. So what we're supposed to find is the rate of change of area. Well, once again, we need to write that in calculus ease. That is, we need to write that the derivative of A with respect to t is what we're supposed to find here. But we're supposed to find it a little more specifically than that. When the radius is equal to 4. So that's a little more information. Okay? Now, the next thing we need to be able to do is we notice that the two variables involved, okay, we need an equation. And we need an equation that relates the two variables that have the related rates. See, we have a variable r and a variable a representing area and r representing radius. And so we first need an equation that involves those two variables. Well, in this case, it's just the area of a circle equation. What is the area of a circle? Area is equal to pi times r squared when we're talking about a circle. So we have our equation that relates the two variables. But now we need an equation that relates the two rates. And that is the two derivatives. And so the way we accomplish that is that we take the derivative of both sides of this equation with respect to t. So we take the derivative of the left side. Actually, I should probably do this a little differently. We'll take the derivative with respect to t of the left side, and we'll take the derivative with respect to t of the right side. Now, when we do that, we're going to create a relationship between the two rates that we have above. That is, the derivative of a with respect to t, we can just simply write as dA dt, can't we? Now, over here on the right, though, we need to remember that pi is just a constant. It's not 3.14, but it's approximately 3.4. You know, that could be like the derivative of 3r squared with respect to t. So that's really the constant times the derivative with respect to t of just r squared. Now, in this case, of course, here's what we have. The derivative of r squared with respect to t, because it's with respect to t, what do? We bring down the exponent 2, we decrease the exponent by 1, and then we multiply with the derivative of what's inside the parentheses, the r stuff, and we've already seen this several times. That's the derivative of r with respect to t. That's basically the chain rule, or the general power rule in this situation. So let's rewrite that just a bit. We have the derivative of a with respect to t is equal to, let me write pi times 2r as 2 pi r times dr dt. Now, we finish this off by saying, look, when r is equal to 4 was the question that we were first asked, isn't it? When r is equal to 4, and we know that derivative of r with respect to t is 1, okay, is equal to 1, isn't it? Okay, then at that time, the derivative of a with respect to t is going to be 2 pi times our r value of 4, and we know that the dr dt, the rate of change of the radius with respect to time, is just 1. And so that ends up being what? 8 pi? Which is approximately, let's see, approximately, and I didn't write the units in here, did I? 25, and I'll say 0.12. What did I do? I approximated pi at 3.14, and then I just did the calculations. But that's approximately 25. Now, what are we talking about? An area, aren't we? But the rate of change of area. So area is, in this case, square feet, and it's changing per, what do we have here? Per second. Okay, because up above, remember, we were changing at 1 foot per second. So the rate of change of the area when the radius is 4 feet is about 25 square feet per second. That's about how fast it's changing. Now, what I'd like you to recognize is that if we had a different radius amount, then the rate of change of the area would be different. Okay, so let's kind of look at example 1b, and we'll just change a bit here. Well, this is basically the same problem, except now the question is, what is the rate of change of the area when the radius is 10 feet? And now let me remind you, we've already done all of the work, and what we ended up with is derivative of a with respect to t, that's the rate of change of the area, is 2 pi r times the derivative of r with respect to t. And recall, of course, remember that we're told that the rate of change of the radius is a constant amount. And with time, it's not mattering, it's just changing at 1 foot per second. Okay? But now we want to know what the rate of change is when r is 10 feet. But when r is 10 feet, then what do we have? The derivative of a with respect to t would be 2 pi times our r value, okay, which is 10 in this case, and times our constant rate of change, which is still 1. Well, that ends up being what? 20 pi. And that would be approximately, what would that be? Well, let's hold on just a moment. Yeah, my calculation tells me that's approximately 62.8 square feet per second. Now, so when we have a large, basically more time has passed, hasn't it? Now, we're not talking about what is the area of the circle. We're talking about the rate of change of the area of a circle. 62 square feet is not the area of the circle. But here's what we would have. Here's the situation that to make a little sense of this. When we have a small circle and we change that radius by 1 foot, okay, then you can see, of course, the area of the circle certainly got bigger. But when you change a circle that is already pretty large by a radius of 1 foot, what's happening is, so when we do this, we change that radius by 1 foot. The area that we added was all this area here, wasn't it? And that's a lot more area than we would add here. So that rate of change, just in that 1 second, we added a lot more area. And so that's the idea of why this is a much larger rate of change. That area is increasing the rate at which it changes. Well, what I'd like to do is summarize a couple of things here and give you a couple of warnings. Let me get set up for that. Well, let me start, and this may be a little halted as we go through here, but here's the insight that I want you to have, because this is where students make a mistake when we talk about related rate problems. And the thing is to notice the order, or when we use the radius amount. In the first example, 1A of 4 feet, and the second example of 1B of 10 feet. And here's what I want you to recognize. First, we use the equation, in this case, A is equal to pi r squared. The first thing we did was to use it to create an equation that related the rates, that related derivative of A with respect to t and the derivative of r with respect to t. That's the way we use that equation. What we didn't do is plug in the radius amount to that equation. And it was after we have the equation, we used the radius amount in the equation derivative of A with respect to t is equal to 2 pi r times the derivative of r with respect to t. That's when we use the radius amount. And the reason for that is it's important that we do it in that order, because otherwise we wouldn't come up with a meaningful result. And here's what I mean by that. If we substitute r equal 4 into the original equation, A is equal to pi r squared. See, if we substitute it in there, then that has in effect, okay, what would we get? We'd get A is equal to pi times 4 squared, or A is equal to 16 pi. In effect, what that does is it stops the ripple from gaining size. We freeze time. See, we freeze time when we do that, because we're looking at specifically when the radius is 4, and that's that frozen point in time. And when we freeze time, you know, when we're stopping time, then basically the rate of change of something that's stationary is 0. So that's the problem. This is the rate of change then. The rate of change of area or any other value, rate of change of, in this case, area, when time is frozen, okay, or when time is frozen, is 0. See, what would happen here, if we tried to get a relationship or find out about the derivative of A with respect to t here, well, 16 pi is just a constant, and we'd get a 0 value. And that's really the whole point, that this r is changing and this A is changing, and we can't freeze that. If we do, then we're stopping the changing, and so then the rate of change of area is just 0. And so we use the equation to get a relationship between rates of change, and that's the equation we put the r into. Now, I know this maybe seem like a lot to remember, but as we do a few more problems, then I think it will fall into place. We just need to be careful not to substitute in fixed numbers for variable amounts until we get a rate of change equation. Well, this is the end of the introduction. Next, I want to look at some problems, and we'll start out with the first set of problems with kind of a recall the steps that we need to go through before we do the problem.